Okay. So last class we finished the construction of all finite fields, and we've defined this object Fp bar as the union of all finite fields of that characteristic, and this also happens to be a field itself, which is now infinite. Any questions till this point? Yes. Sorry, where? This one. Okay. No, the lemma 1 statement is clear. Okay, what is the setting? This one probably. Gx is degree t irreducible. Yeah, so then anything below t, x to the p to the t minus 1 will not be x, and also anything smaller x to the p to the e will not be x. Well, it's the same proof. You take t minus 2, you get the same proof. Sorry? No, you instead of t minus 1, you just put e there and see the proof. It's the same proof. X to the p to the t minus x, the GCD you will take. You will put here this polynomial instead will be x to the p to the e minus x for e less than t and positive. That is what you have to consider in the GCD. And then x to the p to the t and x to the p to the e, the argument will be the same. You will again get a contradiction. And the only place where it will hold is equal to 0, which will be the contradiction. This essentially is t minus 1 equal to 0. This in general will become e. So it will contradict that e is between 1 and t minus 1. It's the same proof. I just took t minus 1 as a. Oh, no, it's p to the e. You keep. See, the point is that. So here, what did we learn? That well, so this calculation has to be redone. So if it was t minus 2, then you will get x to the p to the t minus 2 times p square, and which will become x to the p square minus x. Okay, well, let's do that afterwards. maybe I'll add that in the notes when I publish it. Any other question? That gap we'll fill. Anything else? Okay, so then we'll start with the application. So just to, okay, let me, yeah, so just to recall this model, because it's a new problem, it's an inherently computer science problem that you have a person A who wants to transmit a message to person B through some physical channel, which is in which errors could be added. Error basically will be that when you send a binary string, some of the bits may get switched or flipped. 0 becomes 1, 1 becomes 0. Or in general, if your message is over some alphabet, then some of the alphabets will get switched. So A may become B, B may become D, and so on. And also this message may not be any meaningful thing. It may just be like a password or something which doesn't make sense. So the thing is that every letter or every bit that reaches B ultimately, I mean, there should be a way for Bob to find out what was the correct M that Alice wanted to send. Approximation will not work. So there is a mathematical solution for this, which will use finite fields. What is done is that this message M is first encoded, and then it is decoded on Bob's side. Okay, so instead of encryption, decryption, which was for security, here we'll use encoding, decoding, but these two are again algorithms. Just the name has changed. The purpose is not secure, but error correction should be possible. So maybe we see a trivial example first. So suppose on a channel the number of errors is 1. Let's use, instead of fraction, channel makes less than equal to half errors. And you want to send, so A wants to send the string, let's say God. Okay, so so out of these three, I mean, if these three letters are sent, then the problem is it may, at least one of them will get corrupted. So for example, God sent, but when it reaches Bob, then it becomes Go. Right, and then Bob has no way to understand what did Alice wanted to send, right? It can just change to another word, and there is no other information. So is there an easy way to correct this? If you just wanted to send God on an erroneous channel, what encoding should you use? Right? We don't want a general algorithm. Just for this, what else can you do? What else can Alice do? So Alice can send God, first encode it into GGOODD, and then send it over the channel. Will this be okay? This also is not okay, because maybe what Bob gets is gets is this. So now Bob has the understanding that there are these blocks which were sent. So Bob can understand that O means O, GG means G, but then GD could be G or it could be D, right? There is no way to deduce which one. So it could be either dog or it can be gog, right? Or maybe meaningful is just this doesn't change. Sorry, this was wrong. Yeah, the second and third blocks are uncorrupted, but the first one got corrupted. So a single G became D. Yeah, so it can be either God or Dodd, right? There is no way to distinguish which one Alice meant. Can you do something better than this? Well, you can copy it 3 times. Then what can happen? Is there a way that in every block, maximum 1 letter gets corrupted, but still Bob has a way to decode? Now it is, right, because only 1 can get corrupted out of 3. So it becomes GGD or OOU and DDE maybe. But if you look at the blocks, then in each block, Bob can just take the majority vote, right, and then deduce that first is G, second is O, third is D. So this is called the repetition code. So repetition code just repeats every letter. So if the number of errors is T, you should repeat it how much? You should make it 2T plus 1, so that majority vote will give you the correct answer. So for errors, number of errors less than equal to T, it requires repeating a letter 2T plus 1 times. Okay, so which means that K length becomes K times 2T plus 1. So a message of length K will blow up by a factor of 2T plus 1. Usually this T will be quite big, so this means that it's very inefficient, because if you are sending, let's say, a movie, then it will require you to send 10 times the movie, right, which is just impossible. So this won't work physically. In practical applications, this is useless. It's okay for small messages, but you cannot send big data using this, because you cannot even send 2 times, forget about 2T plus 1 times. So this is not practical. So the question is, can you do better? So okay, this will be N. So what you want is that the blow up from K to N should be small. It should not be like this multiple. So can you make N closer to K? So obviously N equal to K will again not work, as we have seen, but maybe N equal to K times log K is one possibility. Right, this will not be considered too much of a blow up. Well, this can still be more than double, but Yeah, let us first check this. So in the previous application, t could have been very close to k, and then it's giving you k square. So let us try to handle that first. Let us try to go from k square to k log k. Okay. So these things at this point are not clear because you haven't seen any code except this repetition code. So we want to design better and faster encoding together with a decoding algorithm. Okay, so this is the general goal in error correcting codes or in coding theory, that you want a fast and efficient in the sense that n over k is not too big. You are trying to optimize that. So you want this fast encoding algorithm and you want a decoding algorithm also. Just saying that you have encoded is not enough. Bob should also be able to decode in the presence of errors. Right? So decoder will not get the correct code, it will get something which is a corrupted version of the code. So this will be for code plus error. Okay, so yeah, unfortunately decoding is a trickier thing. What I can show you is an encoding algorithm using the finite fields that we have constructed. Okay, how that is decoded will take more machinery, so we will not do that in this course. Let us just show you one interesting encoding which is far more clever than just repeating letters. It will be very algebraic. So what we will do is think of the message as a string in fp to the n, fp to the k. Okay, you can also think of p as 2. Okay, in that case, maybe I should take this to be q, where q is equal to p power and p is prime. Okay, so in case you want to work with Boolean, so p is equal to 2, then you should pick a power of 2, let's say 2 raised to d, construct that finite field f 2 raised to d, and your alphabet is that. Okay, so in your message, your A is basically the field element, and B is a field element, and C is a field element, and so on. Okay, so as many field elements, as many letters in the alphabet. So key of these letters form your message. That's the message that Alice wants to send. What is encoding? So encoding will be a map which will take a message and make it into it will encode it into a code with n length n, so n will be obviously greater than k. Okay, the message will blow up. We want to blow it up as small as possible. So what is this? So you have let's say you have A0, A1, AK minus 1. Right, so these are the k elements in the finite field FQ. That is the message. The code word will have n elements. So what these n elements will be is of course the central question of design here. So what is done is that you use A0 to AK minus 1 to think of a polynomial. So consider polynomial fx to be A0 plus A1x, A2x square, up to AK minus 1, xk minus 1 plus xk. Okay, consider this polynomial. So now basically the polynomial is capturing your message. The message A bar. This defines the polynomial, and the polynomial conversely defines the message. What do you think are the BIs then? You think of your message as a polynomial and you send to Bob what? You just evaluate the polynomial at many, many points and send the evaluations. Okay, that is the code. So B0 will be f at, okay, let the field FQ have these points alpha 1, alpha 2, dot dot alpha n. So pick these elements alpha 1 to alpha n in the field. So for example, you can think of these as just alpha 1 is 1, alpha 2 is 2, alpha n is n. Okay, you can just pick the first n elements. In the simple case, they will be numbers. In the complicated case, they will be elements of the finite field which can be polynomials themselves. But you can pick any n elements and then B0 will be f on maybe let's use alpha 0 will be alpha 0. B0 will be f alpha 0, B1 will be f alpha 1 and Bn minus 1 will be f alpha n minus 1. Okay, so the code that you will send over the channel is just many evaluations of the polynomial that comes from the message that you wanted to send. Okay, so it's a completely algebraic code. And why is that good? So yeah, so again what E is doing is it's sending A0, A1, AK minus 1 as the evaluations of the polynomial. Okay, we haven't specified what n will be. We'll do that soon. But the idea is such simply this. After that, you can do some parameter fixing, what will work good for in practice. So this is an element in FQ to the K, and this is an element in FQ to the N. Is that clear? So this is the encoding mechanism. Okay, now what do you want in error correcting codes? So the channel will make errors, which means that the channel will corrupt some of these BIs. So it will corrupt some of the BIs, but it won't corrupt the others. When this will reach Bob, Bob will not know which of the BIs are correct and which of the BIs are wrong, right? But yet you want Bob to be able to reconstruct F that Alice had wanted to send, right? So you want this property in the decoding. Okay, so let us first prove a property that's key to this construction. If messages F and G are different polynomials, if messages FA bar so A bar and A bar prime are different messages that Alice wants to send. So if this yeah, let me shorten this, let's call this FA bar. Messages are different, then FA bar and FA bar prime differ in how many places? That's what you have to analyze. So for two different messages, if you look at the corresponding codes, they should be very far apart, so that even if there are errors introduced, they remain different, right? So based on that calculation, you can reverse engineer and say that I have a code that can handle so many errors, right? So first you have to calculate what is the number of places or coordinates in which FA bar and FA bar prime differ, which is same as saying that if you take two different polynomials of degree monic polynomials of degree k, and you take their n evaluations, how many of the evaluations are different? What is that? So this is n minus k plus 1. Let's prove this. So FA bar and FA bar prime are the same at ith place if and only if FA bar at alpha I is equal to FA bar prime at alpha I, right? Basically at the ith place the value is coming from the evaluation at alpha I point, alpha I element in the finite field. So these two are equal, you are saying. What does that mean? So this means that if you look at the polynomial difference or the polynomial of difference, that's 0. Let G be the polynomial. What was that? Capital X. Okay, so consider the polynomial which is the difference of FA bar and FA bar prime. So when you say that your code is equal at the ith place, what you are saying is that G of at alpha I is 0 or alpha I is a root of G. Is that clear? This is simply a translation of whatever we started with. So what is the, how many roots can G have basically? This is what you are interested in. Yeah, so number of equal places is gives number of roots of G. Okay, so the places where FA bar and FA bar prime are equal, it basically gives you that many roots of G also. So if you can upper bound number of roots, you can upper bound the number of matches. So what is the number of roots of G? No, it's not K. Yeah, FA bar minus FA bar prime, the x to the k cancels. So the degree is only x to the k minus 1. The degree of G is at most k minus 1, which means that the number of roots of G is less than equal to k minus 1. Okay, which means that FA bar and FA bar prime differ in n minus k minus 1 places. Is that clear? So what we have shown is that if Alice wants to send two different messages, then the corresponding codes are very far apart. You have a bound on how far apart they are. So this is called the distance of the code. So what we have shown is this theorem. This is the Reed-Solomon code. So I'll shorten it to RS. So the Reed-Solomon code has distance n minus k plus 1. Okay, I will not define distance, but I hope it is clear now. Distance is just that for two different messages, you look at the corresponding code words and what is the, in how many locations are the two code words different. That is the distance. I mean, you have to go over all possible pairs of messages and then pick the minimum. Okay, that will become the distance. So that you have a guarantee that no matter what the two messages are, the code words have this much of minimum distance. Any questions? Okay, so now how will you use this? In the presence of errors, how much should K and N be? So let me call this distance delta. So it's an K and delta code. Okay, so it takes a message and also the field. So the code basically takes a K length message over the alphabet, which is a finite field FQ, and it blows up into N length message in the same alphabet. And the guarantee is that the distance between two different codes is minimum delta. Okay, this is what we have shown. So let's see a picture of this. So what I am drawing here is for two different messages. So CI is just the encoding of a message. Okay, so Alice wanted to send message M1 or message M2. The corresponding codes that she will send is C1 or C2. Now, when it is being transmitted on the channel will corrupt it and it will become some other string. So let's say it becomes C1 prime. And this will become some C2 prime. And what are these balls? So these balls are of radius delta. And what is the space? The space is FQ to the N. Okay, so we are looking at this fancy space which is over a finite field FQ to the N. So these are basically N tuples of field elements. Okay, and there is a notion of distance. So between two N tuples, the distance is the locations in which they differ, right? So using this notion of distance, we can draw balls around C1. So there is a delta ball, the ball of radius delta around C1 and similarly around C2. Yeah, shouldn't call it delta. That's the thing. This will be delta by 2. I want delta by 2. So that all I know is that between C1 and C2, the distance is minimum delta, right? So if I draw balls around C1 and C2 which are of radius delta by 2, and furthermore if I assume a physical channel where the erroneous code word that Bob will receive lie in these respective balls, right, then Bob should be able to get C2 from C2 prime and C1 from C1 prime. What would happen if Bob gets this, a point which is right here, let's say C0 prime. If Bob gets C0 prime, then it is impossible for him to deduce whether it came from C1 or C2. Is that clear? So that is the picture that you want to keep in mind in coding theory, that this is the central problem, that if a code transmitted message gets corrupted too much, then it's impossible for Bob to get the message. But if it is corrupted within the ball, then there is a unique way to get the message. So Bob can, theoretically, deduce C1 from C1 prime and C2 from C2 prime, but cannot deduce anything from C0 prime. Okay, so exact message cannot be deduced from C0 prime no matter how powerful Bob is, right? It's not a question of efficiency, it's a question of information theory. Because C0 prime is equidistant from the two code words, so it could have come from anything. That's the same problem which you saw in the trivial example that we started with, that if GOD becomes GOO, then it is impossible to find out whether Alice meant GOD or Alice meant GOO or Alice meant something else, right? Because there is no extra information attached. So that is what you get in this geometric picture. Okay, so now how many errors can Bob handle with your code? Less than delta by 2, right? That's what you learn from this. So this K and delta code is good up to delta by 2 errors. And delta by 2 was n minus k plus 1 by 2. So these many errors in length n. Okay, so this is the practical result you get. At least for theoretical decoding. We haven't seen how the decoding will work, but at least theoretically, Bob will get the correct information as long as for this n length transmitted code word with errors has errors less than n minus k plus 1 by 2 places. Okay, so out of n, this is less than 50%. But the point is that if you want errors up to 49% to be handled, it can be handled. You can just pick KNN accordingly. Okay. So let's check that calculation. For errors 0.49, so 49%, what you would want is you would want roughly this to be equal to n minus k plus 1 by 2n. Okay, and you can solve this for k by n. In fact, let me just make this n minus k. So what is the answer? So 0.02 n is equal to k, which means that n is equal to k by 0.02. Okay, which is 50k. So what this is saying is that if you want to be as ambitious as 49% errors, even that is decodable by this code. So what it will do is that it will stretch k length message to 50k, and then the corruption in those n places that are being transmitted can be as high as 49%, and still decoding will be possible theoretically. Okay, so from the corrupted code word and hence the message can be found out. So that's the Reed-Solomon code, or at least the encoding. Decoding you have to read separately. That we can't do in this course. But I can still state that Reed-Solomon code has a fast decoding algorithm also. Okay, so both encoding and decoding for Reed-Solomon code can be done very efficiently. So this or variants of this are what are used in practice. Any questions? Okay, so that was the application. So time to move to a more complicated topic. But let me just point out some things that last class students discussed. Well, this thing you can read on your own. So just for fun, you can read what the decoding algorithm is. How can you learn a polynomial from corrupted evaluation values? Let's go back to an example of finite field that we saw last time. This finite field F4, which we constructed as follows. Right, so in the F2x polynomial ring, you do mod x square plus x plus 1 arithmetic, you get a finite field of size 4. Now what you can do is you can study polynomials over this finite field. So for example, you can look at the polynomial y square plus y plus 1, which is a polynomial in the polynomial ring above this finite field that we have constructed. Okay. So that's a new polynomial with complicated interpretation, but it looks simple. It is just phi square plus plus 1. What you have to understand is the following thing. What are the roots of this polynomial f in the finite field f4 that you have constructed? So for in particular, is this polynomial irreducible over f4 or does it factor? Is this polynomial irreducible mod 2? Mod 2 it is irreducible, right? This is what we said for x square plus x plus 1. So mod 2 it is irreducible, but what about f4? As an f4 polynomial, is it reducible or irreducible? Yeah. So this has roots. So it has roots. It has roots x and it's a quadratic. So if it has one root, it has two. What is the second one? Sorry? X plus 1. Yeah, or x square, the same thing. So what you get is that this polynomial is actually y minus x times y minus x square. Okay, this is the factorization of this polynomial over this brand new field that we have constructed. Okay, so x square x plus 1 was used to be irreducible mod 2, but when you go to this new field, there it actually factors. It factors into y minus x and y minus x square. Is that clear? X and x square are the roots. So this is what happens when you go to this bigger field. Certain polynomials which were previously unsolvable are now solvable. Okay, so that is why I said that this behaves like complex numbers. So how do we say this? That's like going from r to square root of minus 1. Let's just say this, okay, which is how you constructed complex field. So the way you constructed complex field was that you wanted to solve x square plus 1, you cannot solve it. So somebody very intelligent decided that just attach square root of minus 1 and that gives a bigger field, and that is the field of complex. Okay, so this basic trick is what we are doing now in a very algebraic and formal way. Okay, so every bigger field that we get, that's like a construction of complex over reals. That is what I meant when I said FP bar is the new complex. Any questions? Okay. Field of what polynomials? Yeah, that's a good question. Will you? Once you have attached square root of minus 1, what will you attach to complex to get a new thing? I don't want to answer that question here, but that is the flaw in your argument. So you, by this f of y, you will not get a new field because its roots are exhausted. You have to do something new. That will require another course. But here we stop at this point. So So what we'll do next is this topic, which is huge in its own right, which is called groups. Okay, so I mean, I could have done groups before fields, but somehow fields are more important in computer science. Groups are another layer of abstraction. So what happens in groups is that instead of two operations that you had in a field, now you will have only one. Okay, so you have to make do with one operation, but that operation will be very nice, it will be very algebraic, it will have what you had with addition, for example, which is you can add two things, you can subtract two things, you can do minus a, you have a 0, and so on. So it's like fields, but with one operation. Okay, and it's also almost as important as fields because I mean all these symmetry studies that you will do in physics or in computer science, the symmetry studies will always give you a group. Okay, or if you work with matrices, that will give you a group, that will not give you a field. So group is also a very fundamental construction. Symmetries of an object. So we'll see examples, but one example you already know. When you hear the word symmetry, you are reminded of permutation, right? So you have 10 elements. When you say that the number of permutations is 10 factorial, so this set of 10 factorial permutations is not just a set. It's not an arbitrary set, right? It is a very special set because any two elements in that set gives you a third element, which is you apply them consecutively, right? So first element is pi 1, the second is pi 2. So you can first apply pi and then apply pi 2. And this is a new permutation, it's called pi 3, right? And similarly, if you have applied pi 1, you can reverse it. You can multiply it by pi 1 inverse. And you will get back what you started with, so that's an inverse. What is the identity in this set? Yeah, if you do nothing, which is just basically send 1 to 1, 2 to 2, 3 to 3, n to n, 10 to 10. That is also a valid permutation. That's the identity permutation. So symmetry is naturally a set with one operation with the best possible properties, but there is no second operation. You cannot add. You can multiply two permutations. Well, you can compose two permutations, but there is nothing else you can do, right? So which is why groups they need to be defined. We cannot just work with fields all the time. So yeah, let me define a notation that I'll need for permutations. So there are many ways to write it. Say 3 elements you want to permute. So the longer way is you write something like this, which is basically saying that in the first one, 1 goes to 1, 2 goes to 2, 3 goes to 3. In the second one, 1 goes to 1, 2 goes to 3, 3 goes to 2, and so on. That's one way. I'll use a more systematic way, which is I'll write this as identity. That's the identity permutation. This I will write as 2, 3. where what I mean by 2, 3 is that 2 goes to 3 and 3 goes to 2. Okay, this is more compact. Save me some time here on the slides. And let's see something more challenging. So this will become what? Yeah, so 1 goes to 3, 3 goes to 2, and then 2 goes to 1. Okay? So I'll use this notation to describe a single permutation map. So this is the cycle notation. For permutation. Okay, so I'll represent a permutation as a combination of cycles. Maybe one more example, because one thing is missing in this, which is 1, 2, 3, 4. Let's say this one. What is this in that cycle notation? So 1 goes to 3, 3 goes to 1, and then you write a new cycle, which is 2 goes to 4 and 4 goes to 2. Okay. So in general, you will have these disjoint cycles written together, and that is a very compact way of expressing a permutation, what the permutation is doing, instead of this more cumbersome where you write element by element the map. Yes, so this set of permutations is called on 1 to n is called Sn. Okay, so this is the symmetric group on n elements. So I think at this point I can define a group formally. So what is a group? So a group is a set such that there is a long list of axioms as you experienced before for fields. So first property is closure. For all pairs of elements AB, A times B, okay, maybe I should give the operation here. G is a set with star such that so the star is a binary operator. It takes two things and gives one. Like for example, AND is binary, OR is binary, so similar thing. Addition, multiplication are binary. So A star B should be in G also. Okay, so two elements give you a third element. It may be the same or it may be distinct. Second is associativity. So this was already mentioned in the case of field, but here we formalize it. So associativity says that for any three elements ABC, it will not matter how you parenthesize. Okay, so A comes first, B second, C third, that order you have to fix, but after that how you parenthesize won't be important. So you can compute AB and then C, or you can compute BC and then A on the left. Okay, these two things are the same. That's associativity. Bracketing is unimportant. So we can just write it as A star B star C. Okay, because it won't matter how you multiply, so we can just, whenever I write A times B times C, I mean the first one or the second one, it doesn't matter, whatever you like. Third is there should be an identity element. There exists an element which we'll call E in G, such that for all A in G, what is A star E, E star A, both are A. Okay, I'll not call it 1 or 0 because I mean this star I want to keep it abstract, because sometimes it will be 1, sometimes it will be 0, sometimes it will be something else, right? So I don't want to confuse with 1 or 0, but you can think of it like the identity permutation in the permutation set. And when you have identity, you should have inverse. So for all A in G, there exists an A inverse in G, such that A star A inverse and A inverse star A is what? It's E, right? That's the condition of inverse. So that is what a group is. So yeah, let's just remark here that Sn with composition is a group of size n factorial.